Hello, welcome to this overview demonstration of the IBM Rational Solution Engineering Lifecycle Management. My name is Travis Siegfried and I am a technical enablement leader for our IBM business partners. Throughout this demonstration, you will see how you can conquer unprecedented complexity inherent in development of smarter products and systems by making better use of your engineering data. Today's smarter products are very complex. Projects require collaboration across multiple engineering disciplines. The artifacts produced by different disciplines are created in different formats, using different tools, stored in different repositories, usually scattered across organizations. And yet very few products start from scratch. There is a continuing drive to reuse existing artifacts, and locating these artifacts and understanding which are available at a particular time are often a manual task, searching each repository in turn to find what you need. Rational Engineering Lifecycle Manager, or RELM, is a new addition to the Rational Solution for Systems and Software Engineering that allows organizations to visualize, analyze, and organize engineering data in order to quickly find information, understanding the impact of change, answering key engineering questions about complex products and systems they're building, all through a standard web browser. Visualization capabilities provide new perspectives on all your engineering data, help your team make different effective decisions. You can even get real-time insight into your status of projects and development of products and systems, helping to support readiness reviews at key milestones. Analysis capabilities help teams to quickly find relevant information, identify dependencies across the lifecycle. Engineering artifacts can be organized according to the products, systems, subsystems, components, and capabilities that you're building, giving you the data that's essential in the right context. For example, it becomes easy to find all of the requirements, tests, and design artifacts related to the heads-up display unit of the Japanese variant of the 2014 model of a vehicle. Documents can be generated containing data from across the lifecycle to support audits, prove compliances, and deliver specifications that form the basis of contractual agreements across the supply chain. RELM is built on a platform that is constantly monitoring and indexing changes in underlying engineering tools so that the data you see is real time. RELM is tightly integrated with the Rational Solution for Systems and Software Engineering, including requirement management, quality management, defect and change management, and architecture and design. RELM leverages open standards and a linked data architecture to enable the integration of data from other engineering disciplines, such as electrical, electronic, and mechanical, and so on. So let's see how this works in practice. Let's look at the automated meter reader system. This is a sample complex systems engineering project. It has task management with work items and change requests, requirements management with stakeholder requirements and systems requirements, along with requirements for various stakeholder and systems components of the product, subsystems and components of the product. It has design artifacts, test plans, test cases, and test results. We're going to use RELM to explore the data for the project, centered around a specific scenario, that of requirement change. Here, we are in the task management. We are in task management application of the project. In the list of high priority change requests, we can see one that is concerning the determining the impact of change to leak indicator requirement here. This change request has been raised because of a change to a requirement that involves the leak detection mechanism specific to a U.S. market. Here on the Links tab, we can see other artifacts that are related to this change request, including the original stakeholder requirement that prompted it. That requirement is in the requirements management application, but we don't need to open it. We can simply see the details with the rich hover over. Now, let's switch to RELM and explore the project artifacts from there. Let's start with searching. The search is up in the upper right-hand corner, and this is because this tool is extremely connected and linked, the search capabilities are extravagant. As you can notice, here we're searching all artifacts that contain the word leak. We get instant results, and if the one we wanted was in the list, we could navigate straight to it. But there are over 100 results, so we're going to dig deep, much deeper. The artifact types are highlighted on the left, allowing us to quickly narrow our results and find the artifact we want, the stakeholder requirement that prompted the change request. We can see the details of the requirement directly here in RELM without needing to navigate to the requirements management tool that holds it. Of course, the search results are not limited to data from irrational tools. It's also possible for RELM to index data from other homegrown or third-party tools, such that searches like this will also find information from those systems. And RELM will only show engineering information that the user has permission to see. RELM is an ideal entry point for different stakeholders across the lifecycle. We can construct queries to answer complex questions that rely on the union of information across multiple engineering domains. This simple example highlights work items in the task management application that have test cases against them in the quality management application. We create views to present different perspectives over related engineering data to provide relevant information to different stakeholders in the engineering organization. They give the data context and are completely configurable according to your needs. Views are ways of visualizing queries, and as such are incredible, powerful, and flexible. This example shows a customized V process for embedded software development. All of these boxes are high-level tasks from the task management application that are related to the change request we are investigating. Of course, views can contain any type of artifact, not just tasks. RELM views can be connected in a network to provide drill-down capabilities across different levels. If I open the view that's linked to this change request, I can get a visualization of the breakdown of those child tasks. From any of the RELM views, I can navigate directly from an element to the actual artifacts in the tool that manage them. Here's the linked change request back in the task management application. The underlying data sources publish their changes to a change log in real time, and RELM is constantly monitoring these changes, the change logs, and the updated dates in near real time. This means that when a change occurs in the underlying tools, The searches, the views, and other capabilities in RELM are always representing up-to-date information across the engineering lifecycle. The quality expert Philip Crosby said, "If anything is certain, it is that change is certain." This is especially true in today's complex systems. Requirements are continually changing and evolving. A change to a requirement may impact downstream systems design, hardware, and software development, and even finished products. If a company changes a supplier for a part, this may impact the upstream system's design and threaten the project's ability to meet a requirement. To be able to effectively manage a change, it's essential for the business to be able to understand exactly what its impact will be, what changes will need to be made, and who will make those changes, and how much it will cost. RELM allows you to visualize, understand, and effectively communicate the impact of a change to any of the artifacts involved in the lifecycle project. One way to analyze and understand the political impact of this artifact changing is through an impact analysis diagram. The RELM impact analysis tool allows us to visualize and interrogate relationships between engineering artifacts. Again, we can do this regardless of where those resources are stored and managed. We can easily instantiate an impact analysis from within our search results screen. The default profile will collect any downstream artifacts impacted by this requirement to a depth of 2 levels, but we can define exactly what kind of analysis we want. So I'm going to close this and select up to 5 levels. The result is an interactive impact analysis graph centered on the source of our analysis, the stakeholder requirement. The lines between the resources are annotated to tell us more information about the type of relationship. For example, we can distinguish between parent-child relationships, blocking relationships, satisfaction relationships, dependencies, and so on. We can easily navigate around the analysis graph and zoom in and out as we wish. We can easily see the type and numbers of artifacts impacted by this requirement and easily navigate to one of them. We can define reusable configurations to filter data in a rule-based way, but we can also dynamically exclude results, allowing us to declutter the analysis and focus on the impact that's most relevant to us. Here, for example, in this graph, there are a number of test results. We can remove one or all of them from the analysis. Of course, we can add them back to the analysis at any time. Looking at the impact diagram, we can see that our stakeholder requirement is related to a system requirement, which is in turn related to a subsystem requirement for a handheld unit. That is connected to a software requirement for a handheld unit, for the handheld unit. That is in turn traced to an interface in the architecture. and it's also satisfied by an internal block diagram. I can click the interface and get a preview. If we examine the interface, we can see that it was created in Rational Rhapsody. Furthermore, we can take a look at the internal block diagram. If we examine the internal block diagram, we can see a preview of that diagram right here in the impact view of RELM. While a preview may be sufficient, in many impact analysis situations, just like in other parts of RELM, it's also possible to navigate directly to the underlying tool managing the data. In this case, that would be Rational Rhapsody with Design Manager. So I'll go ahead and navigate to that portion of the solution. From here, we could drill down further into the model, and pending further analysis by the engineer, updates could be made directly to impacted engineering artifacts. We could create work items for other team members to analyze further and update them as appropriate, and add components and markups to the model in the Design Manager to start collaborating with the design teams. In fact, you can notice the comments that can be made, and history for that matter. Let's now turn to RELM and take a look at how we can determine which products might be impacted by a particular change. Our stakeholder requirement is linked to this system requirement. We can find out which products are defined by that system requirement by asking RELM to find its use in products. As the name suggests, this provides an easy way to discover any products that we are building that use a given engineering artifact. Expanding the hierarchy, we can see that the system requirement is used in the handheld software component, which in turn is used in 3 different meter reader handheld receiver products. One is the standard handheld receiver, and there are 2 more specific to the US and European markets. These are all the products that we have defined in RELM to help us describe the things we are building. Defining products in RELM allows us to describe logical structures of products, systems, subsystems, capabilities, and components, which then gives us the ability to organize our engineering lifecycle data according to these things so that we have valuable content for our searches, analysis, and queries. For example, the find use operation that we just performed was made possible because we defined the logical structure of our meter reader products and then related our engineering artifacts to that structure. It is this organization of our engineering artifacts that our logical product structure that gives us the ability to answer more complex engineering and artifacts within our logical product structure. For example, the show me all of the requirements tested associated with the 2015 version of the deluxe Japanese variant of our product. The product definition capabilities in RELM are first steps into rational solution-wide capability for product line engineering, but for now are focused on organizing your engineering data across the life cycle. We can even work with you to enable information from your PDM systems to be indexed to allow you to relate your product's physical structures as defined in your PDM systems to be related logical structures in RELM. This can facilitate capabilities such as enabling traceability from failure in physical product instances to originating engineering artifacts such as requirements and tests. Let's now take a closer look at product definition capabilities to get a glimpse at how a product manager or systems engineer might define the things they are developing and organize and reuse engineering data across to those things. All nodes in the tree here are called products within RELM, but can be used to represent any level of abstraction in the things you're building. In our simplistic example, you can see that our standard handheld receiver, as shown here, is composed of an antenna, a battery pack, a display, handheld software, and so on. When we select a product, we can see some further information about it. Here we can see some properties that have been defined to describe the display product, such as the number of pixels. Since products can be reused in other products, for example, our display may be used in several different meter reader types, changing a product property in one place is visible anywhere the product is used. Dimensions. It's also possible to see branch dimensions for a given product. Branch dimensions in RELM are simply specific characteristics that define the differences between variants of your products. For example, you may create product variants for different markets or for different specification levels. For our meter reader, we have variants of the standard handheld receiver for the US and Europe markets. And these variants may differ in several ways or dimensions. For example, we know the U.S. legislation requires the variant of our meter reader for that market provides audible indication of detected leaks, in addition to the standard visible indication required in the European market. In an automotive example, we might create variants of a cruise control component, standard, and radar controlled adaptive, to be specified as options or available in different trim levels. In aerospace, a passenger aircraft may have different seating configurations, cross variants, etc. For any of the items defined in our product graph, we can show an audit trail of its history. This gives us an easy to understand view of the version history of the component, including additions or deletions of subcomponents and changes to property values. Here we can see the base 1.0 version of the handheld receiver, as well as the US and European variants. If we compare US version with the original, we can see the changes. Many of the components of the US version are simply reused from the base version, but the handheld software component was itself replaced with a new branch. If we now take a look at the differences for the US version of the handheld software component, we can see the addition of a new requirement specific to that market. In a real project, we would likely create several tasks now for other team members to address the change in their disciplines. For example, it would be necessary for a quality engineer to create verification and validation tests to cover the new system and stakeholder requirements. And that brings us to the end of the demonstration. We've seen how Rational Engineering Lifecycle Manager enhances IBM's solution for system and software engineering to enable organizations building complex products and systems to visualize, analyze, and organize engineering data across multiple engineering disciplines. This improves collaboration across disciplines, makes it easier for practitioners to follow processes and implement practices, and enables managers and engineers to make quicker and more accurate decisions. Ultimately, all of this helps organizations to develop, deliver systems and software more quickly with improved productivity, increased efficiency, and lower risk. Thank you for listening.